Good morning, Colin.
Morning.
Good morning. All right, thank you. Wait, is that? And good morning, Brandon. Good morning,
Good
Xavier.
morning.
Good morning. Good morning. And welcome back. Oh, and okay. Hold on. Good morning, Anissa. Morning, Ryan. Good morning, Adenelsi. Morning, Maria. Good morning, Michaela. Good morning, Chanel. Good morning, Gaia. Good morning, Alexis. Good morning, Carolina. Oh, am I forgetting? That's every and that's I think that's okay. All right. So welcome back. I hope you've had a break. Um, I did. So I'm not finished with your exams yet. I apologize. I'll put it in the chat in a second for more people, if more people come. I have been working. I'm not done with them yet. And when I say they're not done, I mean I'm not done with all the exams. And to be honest, yours, it's not personal, but your section I'm actually working on last because all the other sections are the same class and yours is a different class. So I can do those a little bit more efficiently. So I apologize. I am moving as fast as I can. I had hoped to finish over the break. I did not. Partly, well, so I apologize. So bear with me. They are definitely a priority, and you will get them back before you have to prepare for a final exam. And someone reminded me, someone reminded me a couple of days ago that the next homework that was due is like a little intense to be due right now. So I just postponed it. And I'll just say this too. I postponed the next homework. Well, I'll say this again when more people. I mean, I hope you did have a break, and I hope you haven't been stressing too much about physics, any of this. Well, I'm going to repeat that. Hold on. Let me just wait till the other two people come in so I don't say this all. Good morning. Good morning, Nasrin. Hello. Hello, Ariana and Nasrin. Okay, I'm just going to say this. I'll try to put this in. Good morning. Good morning. Okay. Um, So I'm saying I'm apologizing. I don't have your exams yet. I'm still working on them. Um, and I've done a lot of exams, but I haven't finished them all. They do take a while. Um, but it's not an excuse. You will get them. And what I'm also trying to say, or what I was just saying, and a couple people came in, is don't I just postponed the next homework till next Wednesday, I think. I'm assuming you'll have, well, I'm planning for you to have your exams before then, but don't, but it's also like a trade, like don't kill yourself over the next thing until oh, wait. Oh, interesting. Wait, there's something in the direct chat about homework nine. It says to only do part four. Okay, wait, let me check that. Well, what I am definitely just trying to lower hand. Wait, is someone's hand up? Oh, that's my hand. Um, All right, I will check that in a second. I am just trying to say, again, I didn't do as much catch up this break as I was hoping. I did a lot, but not enough to benefit you. Um, Again, not personally, just because because I'm trying to be like a factory. And anyway, but they are coming, and you will get them before you have to do a final. Now, wait, I'm just going to look at what someone's saying in the direct chat about the homework nine. But yes, don't kill all you should be trying to do is catch up wherever you're behind in this class. Don't worry about new things until I catch up with you. But wait, homework nine. Let me just see what that's about. It may be correct. Wait, where did it just go? And then we'll get back to material in a second. Homework nine says, oh, part four only. Yeah, that is. Oh, and someone's already turned it in. My God. All right, hold on. Oh, definitely where it says the textbook readings. Don't worry about that. I don't know why that's old. Why does it only say part four? Yeah, okay. No, that is a mistake. It shouldn't just say only part four. You do need to know all the stuff in this whole homework. On the other hand, now that I'm looking at it, you see that it does give you, well, it gives you, it doesn't give you answers. It gives you hints and stuff, which is helpful. All right, bear with me for 1 second. I may or may not, I don't know why it says, I apologize for that. And the person that's already turned it in early, which is great. If that, I don't want to embarrass anybody. If that it's totally noted that somebody turned it in early. I appreciate that. I'm not looking at your particular assignment right now. If you only did part four, I apologize. And obviously you still have time to do the other parts. So hold on. It shouldn't say only part four. Thank you for that correction. Wait, but I thought I changed. Yeah, do what? So it's not doing, so it's due a week and 2 days from now. Yes, good job, person who turned it in early. That is impressive. Okay. I'm going to see one more thing about it. Um, if I can quickly fix where it says to do the textbook reading, I will, but I'm not sure that I can because it's a PDF. Hold on 1 second. Sorry. Yeah, that's weird. All right, I'll try to fix that later. Don't worry about the I'll put, all right, I'll put that in Google Classroom. I'm sorry. I will put that in Google Classroom right now, just in case there's confusion. Huh. Okay. So I want to get back to physics for good or for bad. Um, I have one question for you. Oh, someone's here. Someone's here. Oh, wait. Thank you. You ignored that. Okay, good, good, good. Okay, I'm looking at the chat. Um, and yes, sorry about that. Direct type people who were letting in. Yeah. Okay. Um, um, the gates. Yes. I have one question for you though. And please spread the word. So again, well, I'll say, okay. One question for you. In lab, can you remind me, because I have a whole plan for today, but I will readjust it if my understanding of where you are in lab is wrong. In lab, have you could you quickly tell me in the chat or whatever, um, are you up to lab five and well, are you up to lab five, the slow down lab? And put another way, you are at the slow down lab. Okay, great. And we're going to do week two. Okay, you're doing week two of lab two. Okay, perfect, perfect. That's what I was hoping. That's what I was thinking. And so that means your formal report is not yet due, correct? On lab five. Like you have not turned in a formal nope. Okay, right. Because yeah, how could you? Okay, so the good news is at least even though, again, for anybody who just joined, again, I do not have your exams finished yet, and I apologize, and I will get them. So, again, for anybody who just joined, I'm postponing the next homework further into it will all come out in the wash. If more people join now, please repeat to them, or I'll put in the chat if I get a chance. Um, but what I can help you with, what I can do that will hopefully help you and reduce stress is I would like to now continue the discussion I started before break, a discussion that's meant to be directly um, applicable to your lab five. Okay. So hopefully this will not only clarify things, but maybe even reduce some of your stress or work regarding the lab report. Okay. Oh my God. Sorry. Okay, this has never happened before. I'm sorry. I just got a notification from Zoom that I've never gotten before that says it looks like maybe you get this all the I have a feeling I'm the only professor that gets this. It says it sounds like you might have switched to a different language other than English. Please update so we can provide better quality transcription. All right, that's what I get. Like it doesn't, if Zoom doesn't even think I'm speaking English, there's no way you do. All right, so I will slow down or whatever. Um, so I want to talk, so I'm going back to Newton's second law and free body diagrams and all of that, where we ended, well, okay, where we ended right before break was on the notion of friction. And I do want to continue with that. Like that's a big piece of that plays a vital role in Lab 5. But the other thing that plays a vital role in Lab 5 is angles and how to deal with angles when you're in a Newton's law problem. So that's what I want to focus on now is angles. Um, Now, like anything else in physics, in principle, you already know, like the reason you could even be assigned to do a lab before you hear the lecture is because in principle, you already know how to deal with angles. Like in principle, angles mean break vectors up into components and use sine and cosine and all that. In principle, we already have all the tools we need to do the next step in physics. That is always the case. However, of course, in reality, one needs practice and experience to get used to how old tools fit new situations, right? So, like, I mean, otherwise you wouldn't like need, right? So I want to. So my point, physics doesn't sound right. Physics does not sound like English. That's yeah, and neither do I often, even when I'm not right. Good point. So. Um, okay. Okay. So I'm going to do a couple of quick, comparatively quick exercises to get to the issue of the lab. Okay. Okay. Oh, sorry. Okay. Quick example first. This is not the lab yet. This is to like build to the lab. Okay. So example one, let's say we have a block or a box on a table. Oh, and we'll say a smooth table. There's like, notice I'm not drawing any jagged lines on the table surface. So we're going to start with an example of a smooth table. So we're not worried about friction yet. Mu, the coefficient equals 0. Okay, but we've got this block on the table of 2 kilograms mass. And and we're pulling the block. There's a pull or of 20 newtons. Um, Sorry, yeah. there's a pull of 20 newtons, like maybe some from some string or something like that, or your hand or whatever. You're pulling the block, but you're pulling it at an angle of 60 degrees as measured from the horizontal. And the question is, what is the acceleration along the x-axis, the acceleration along the table of this block? Okay. So, so what do you do? The procedure always is first to draw diagrams, and then, well, here's the procedure. But I'm gonna do it sort of quick to get to the point of the angle. Like the procedure is always you draw a system schema first, and the system schema is here's the mass, the entire Earth is interacting with it, and the table is interacting with it, and um and that hand or that pull or whatever is interacting with it. We'll call it a hand. Okay. That's a system schema. That's to make clear that's to make clear what are the forces acting on the object, what objects are these forces coming from. Um, and the table, if the table, then the table is pushing, it's a surface that's pushing against the block. If it were a rough surface, remember the rule is I would draw two lines for that table, one to incorporate friction and one to incorporate the but it's not a rough table, it's smooth, so I'm only drawing one line. So that's the system schema. Then from that system schema we draw a pure free body diagram. Each one of the lines from the system schema becomes an arrow in the free body diagram, right? So first of all, and now I care about direction. Now those lines, well, now they're arrows because they represent vector quantities now. So the force from the entire Earth points down and becomes the force of gravity, mg, right? The table is pushing up, and it's exerting what we call a normal force on the block, right? And then and then we have the pull of the hand. That's and we draw it in the direction that it's actually going, like that, right at that angle of 60 degrees. So that's it. There's three lines in the system schema, so there's three arrows in the free body diagram. So that's the pure free body diagram. Now comes the issue like that I want to address. Like if I look at that diagram, not every arrow is perpendicular or parallel to every other arrow. Like they're not all lined up along perpendicular coordinate axes, right? So that means I have to break up at least one arrow into components so that everything lies along coordinate axes. Remember, the whole point is that F net equals ma is a vector equation. A vector equation means it's really three simultaneous or two simultaneous equations, one in the x-axis while one other is simultaneously yet independently true in the y-axis, right? So I need axes. And I need everything to lie along axes. So I don't have that here. So what I have to do, so whenever you have this situation, which is often, you have to make a new diagram called a component free body diagram. And for that new diagram, break up, well, so okay. Okay. Now, this is supposed to be a practice exercise, right? It's not the lab yet. It's a practice exercise. Some of you might even think like it's too obvious and easy, but here's one of the reasons I'm doing it right now is to emphasize a huge point that's crucial for the lab and frankly for physics 204. The huge point is this pro tip, okay? We're going to break up one of the vectors into its components, into components that lie along the x and y axes. And I'm telling you right now that in this case, hopefully it's not going to mystify you. Like hopefully you'll like agree and be comfortable with it. Hopefully. But it is a big thing in physics that some of you might even remember from high school. The breaking up vectors, breaking up force vectors from free body diagrams into components, into sine and cosine components, is a big thing in physics. It comes up a lot. And a lot of times, what happens in physics is that people face a tough choice about how to break up vectors and which component becomes sine and which becomes cosine. Again, hopefully it's not like particularly hard in this problem, but it can be. So what I want you to watch carefully in this problem is what the strategy is that applies to all future problems. So here's the first strategy. People often ask, which vector do I break up? The answer to that is any vector that's not lying along axes. And the way to know the answer to that is you first have to consciously choose axes, even or especially when they seem really obvious. Okay, this is like the physical path. In other words, this is Galileo's principle of relativity. Like always, the whole idea is that physics works in any coordinate system, right? In any frame of reference. But therefore, we always have to choose our frame of reference. And especially when the reference frame seems so obvious that it doesn't even seem like a choice, that's when we really want to choose it consciously so we get the muscle memory, A, for future problems, and B, also so that we don't accidentally stray from that reference frame in the middle of while we're analyzing the problem. So, what I'm getting at is this. You might think, well, the x-axis and the y-axis here are obvious. You might think the x-axis and the x-axis is horizontal and the y-axis is vertical. And you are correct. They are. But here's why. Like, because other axes would work as well. You could have a tilted coordinate system and it would still work, but it would just be like completely annoying and hard. Why? Why is it obvious that the x-axis should be chosen like this and the y-axis should be chosen like this? The real answer to that is because we expect the block to accelerate along the table horizontally. Because, and it will, because the acceleration we're solving for, and the acceleration we expect is horizontal, therefore we're going to line up our principal axis that way with the expected direction of acceleration. I'm trying to tell you that the rule of the pro tip is that whenever things get complicated, always choose your principal axis to lie along the direction of expected acceleration. Hint, hint, hint. That's what's happening in the lab 5, right? Like if you really think about it, the reason mg gets broken up, which is confusing to people in lab 5. It's confusing to anybody who actually thinks about it. Some people just like memorize stuff and accept whatever. But so that you see where I'm going with this, in lab 5, the reason we break up mg, even though it seems like it's just pointing straight down, like why are you messing with mg? Because the expected direction of acceleration is along a slant. So we tilt the x-axis. You see, okay, I don't want to get ahead of myself, but to the rule, this will be true for the rest of physics, that strategically you line up the x-axis with the direction of expected acceleration. So that's what we're going to do here. Okay. The and there, so the x-axis will be horizontal, and I mean the positive direction of x will be the positive direction of acceleration. That's equally important. And then y will be perpendicular to that. And if there's a z, it's perpendicular to both of them. Okay, so my x and y axes look like this yellow coordinate system right here. Okay, therefore, once the coordinate axes are chosen, we zoom in on all, you know, um, misaligned vectors, misaligned forces, and resolve into components like you did in the first part of the course. So what I mean is, so now that we know that we're dealing with a regular Cartesian plane, I zoom in on that, right? And I don't even care about the numbers right now. I just care about the concept. Like P is pulling up at this angle, right? So I say, aha, up and to the right is a combination of is the addition of to the right and up, right? Just like and then I do SOHCAHTOA. Cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. So to cut to the chase from what you already know from the other you from pre-midterm, P cosine will be down there, P sine will be there, right? So now, and this is a mistake people always make. So now what I'm saying is for me to pull on the block up and to the right is literally equivalent, mathematically and physically equivalent to someone pulling to the right a certain amount, a cosine fraction of the total amount, while someone simultaneously yet independently pulls up a certain amount, the sine amount, right? Like so now but these two components are now lying along coordinate axes. So I now substitute them and only them into the free body diagram. Like they become a replacement. This is what people always get wrong. They are not in addition to, they are a replacement of the P force, the total P force, right? So the component diagram, so this is our third diagram now. I just want to see if I'm numbering correct. Right. Like you start with the system schema to see what the forces are. Then you go to the pure free body diagram to actually turn those forces into vectors. Then you make, when necessary, which it usually is, you make a component free body diagram, which in this case will look like this. You have normal going up, you have mg going down, and now you got some amount going to the right, p cosine theta, and and some amount going up, p sine theta. With me? And I made it bigger because the number is bigger because we were given anyway, it's not always bigger, but it's bigger here because of the numbers. So that's my diagram. So I've got two forces going up, one going down, one going to the right. That's my component diagram. And I'm about to move on. Stop me if you need to stop me. Um, but please notice one thing. That's a correct component free body diagram, and notice everything in it is like a name of a force, and I tend not to have numbers in there. It's like it's all general functions, so you see the relationships. But one thing you need to notice before I go on is even there, notice there's forces that are not, I mean, there's an odd number. Well, there's an odd number of forces on the y-axis. There's an odd number of forces on the x-axis. Like there's no rule ever in physics that every force that's going one way on an object needs to be balanced by a force going another way. Like that is not what Newton's third law says. I don't want to get myself bogged down. But notice a lot of things are unbalanced here. That's why there's going to be acceleration. Okay, anyway, that's the diagram. Now what do we do? Now, and this is always the procedure for everything. I'm just looking at the time. Now apply Newton's second law to each axis independently, right? This is all the whole. This is still Galileo form number 5. This is vector stuff, right? So, like in other words, we now know this law is true. So what does that really mean? It really means that this is true while simultaneously yet independently. This is true, right? So I'm going to go to the next page and apply them. Now, pro tip. Well, pro tip. They probably pro tip. I'm thinking pro tip. If you're over the age of 50, you probably shouldn't use the expression pro tip, right? I'm just not wearing it well, am I? I apologize. I'm just trying to relate. Um, okay, pro tip is this. Okay, if you're following the pro tips, if you're always lining up your principal axis with the expected direction of acceleration, then when you, yes, yes. Uh, direct. Thank you for paying attention. So someone's in the direct chat asking me, is this what you're asking? Okay, cool, cool. No, thank you for paying attention. So what I'm going to do now, so someone just asked me to turn back. This is F net equals MA, right? But I'm going to apply it now in one axis at a time because that's the point. It's a vector equation, so it applies to all the axes simultaneously, yet independently. Okay, cool, cool. So I'm going to turn the page and I'm going to apply, it's the same equation. Now, hopefully people can see just going to be iterated over the different axes. But my strategy here, and whenever I say pro tip, I'm not trying to be funny. I am sometimes trying to be funny, but when I say pro tip, what I really mean is strategic advice that isn't a physics law. Like you don't have to do what I'm saying when I say it's a pro tip. I mean, I think your problem solving life will be much easier if you do what I'm saying. But I'm not saying it. Okay. So for example, what is true is now F net is going to equal MA on each axis independently and simultaneously. Really, in principle, we now have simultaneous equations that we're going to need to solve. But sometimes if they're really solving simultaneous equations can be a headache. So my strategy is if you followed the first strategy and you lined up your principal axis, your x-axis with the direction of acceleration, then now when we apply F net equals ma to each axis, I'm always going to leave that acceleration axis for last. The acceleration is what we're solving for. That's like what we're actually concerned about. So I always leave the axis of concern for last for a number of reasons you'll see, but not the least of which is it's very frequently the case that we'll get information we need from some other axis and then be able to like use it on the axis that we're solving for. So here's what I mean. I'm going to start with the y-axis. Um, so I'm going to say the sum of all the y forces equals the mass times the acceleration along the y-axis, right? Now, so this is the law. It's always the law. It's a very simple law, but the whole issue of the law of F net equals ma is like it's always about what do you plug in on the left side. It's all about always expanding the left side. Just and where do you get your information? From the very last picture you drew. And I'm telling you again, I'm not to the point of the other pictures was to ensure that this picture is correct. But then this picture is the one you use for the math. All that is a series of pictures that follow an algorithm that, if followed correctly, by the time you get to the third picture, the component free body diagram, the math is set up for you. What I mean by that is the y-axis, I look at the y-axis and like if one direction is positive and the other direction is negative, I think we already designated that. The y-axis is telling me that the normal force is pointing up and some component of the pull is pointing up. And then I don't know why it's doing that. Sorry, sorry. Um, and then gravity is pulling down, right? So I'm adding up That's what that big sigma just means. Add them all up. I'm literally adding them. It's just that mg is getting a negative sign because it's pointing down. Like, right? So I'm adding everything up just along the y-axis, but I'm taking into account positive and negative signs, right? So all of that together equals the acceleration sub y, the acceleration on the y-axis, right? That's what F net equals ma means, right? And you can see this is, I'm watching the clock. It's already starting to look a little complicated. You can imagine it gets more complicated once friction's involved, hence your lab, right? So I'm doing that next. But, well, anyway, so here's a kind of statement of Newton's second law applied to the y-axis. But now, here's why I started with this axis. On this axis, well, well, okay. On this axis, I know there's no acceleration, right? It's just a block or a box that's being pulled along a floor, or I mean along a table, and you're just pulling at an angle because of leverage, like just because like you're a tall human being and you don't want to like stoop down or whatever. But you're just dragging the thing along. It's not going up or crashing through the table or something. So we know that the acceleration in the y direction is zero. Okay. Therefore, Therefore, the rest of these things must be balanced. In other words, the normal force must equal mg minus p sine theta. I'm about to go on, but I'm saying in this case, like what I'm saying is the table is not is not supporting the full weight of the object. N does not equal mg, and I've warned you of this too. Like normal, there's no formula to memorize for what the normal force will always equal, because the normal force won't always equal anything. It just does. The normal force, in other words, the table supports exactly and only what the table needs to support. There's a block on the table. The block has a certain amount of weight, mg, right? A certain number of newtons in the metric system or pounds in the American system. The table would, if the block were just sitting on the table would support that entire weight. But you're pulling this thing at an angle. So to some extent, you're or whoever is pulling up on the block. So that's doing some of the effort instead of the table. Do you see what I'm saying? Like, this is just an example. First of all, how you ever solve for the normal force is you look at the axis along which the normal force is acting. This is how. The normal force will equal mg minus p sine theta. And those are numbers that we would plug in at the end. If the question asks, what's the normal force? It would be what that answer. But the real reason this is, I'm going to go on to the x-axis now. Like that, I'm not going to do anything with that information in this case. But the reason I'm not going to do anything with that information in this case is because the table happens to be smooth. If in the next example, when the table won't be, if there was any friction at all, what we learned 2 weeks ago before break is that if surfaces are rough, the more they squeeze together, the harder it is to rub them along each other. The more the normal force is, the more the friction force is. So we need this normal force to figure out the friction if there is any. And this is another reason I always go to the y-axis first. Okay, but in this case, there's no friction. So I'm just going to move on to the x-axis. The sum of the x forces equals ma in the x direction, right? And now in this direction, there's only one force. It's just p cosine theta, which I got from breaking up that thing, breaking up the vector. So p cosine theta equals max. Okay, so ax, which is what the whole problem is asking for, ax will just equal p cosine theta over m. I always try to save the numbers for last, right? P was given, I think, as 20 newtons. Cosine, well, cosine of 60 is 1/2. I'll just drag this out. M was given as 2 kilograms. right? So it's 10 um, times 1/2 meters per, because cosine of 60 is 1/2, right? So the answer in this case would be 5 meters per second squared. And that's the answer. Okay. And that's a procedure. So the procedure for all force problems: system schema, pure free body diagram, choose coordinate axes, break up all forces so that they lie along your coordinate axes, and then, and the purpose of doing all of that is now, and then, oh, sorry, make a component free body diagram. Once you have a component free body diagram, what that means is you have a bunch of arrows that are all lying along separate coordinate axes. Then you apply F net equals MA to each axis, and to expand the left side, you just copy down the arrows that are from your component diagram. That's a procedure for always. Now, what we have to do here for your lab, um, we have to apply this. I mean, again, in principle, now we're done. Like we could go home, like you, in principle, know what you need to do for that. But I want to incorporate friction now, as you do in the lab, um, and um, and in the lab, your whole system is on an angle, and that leads to this funny, leads to a more sophisticated choice for coordinate system. So I want to look at that with you. Let me just, I'm going to see one. Okay. In order to do that, I'm watching the time. We have 30 minutes. So, okay. I want to do one more step to scaffold this, so to speak. So I'm going to do example two, very, very quickly. Um, okay. So in example two, I'm going to do the same example. Okay. So say we do the exact same example, only now the table is rough, right? So now the table, okay. So now the table is rough and has a mu of, let's say, 0.2. So same question, what's the acceleration in the horizontal direction? So let me show you how that adjusts once there's friction involved. Well, the systems, so I'm going to do the same procedures, right? But I'm going to hopefully do them a little bit quickly this time. System schema, same system schema. You've got the Earth, you've got, and again, it doesn't matter where I draw things. It does matter that it's illegible. But now, if the table is a rough surface, it gets two lines because not only does the table press against the block, but it rubs against it frictionally, right? So that's the system schema now. So the pure free body diagram is now this, right? Oh, and the assumption of friction is Okay. This again is essentially what you would. So I'm reminding you how friction works is the magnitude of friction is the coefficient of friction times the normal force. That's what we said right before break. And I'll play that out in a minute. Like I'll apply it. But that's the magnitude of the friction force. And the direction of the friction force, it's another Galileo thing. The direction of the friction on surface A as exerted by surface B always opposes the velocity of surface A relative to surface B. It's a mouthful. It usually that means exactly what you think it means. If the block is, if the table is exerting friction on the block and the block is trying to move to the right relative to the table, then the friction will push it to the left. Exactly what you think. The friction opposes the motion. It's just that we have to emphasize motion in the relative sense here. And if you're wondering why I care about that, if you care, if this is already boring you, if you want to let your mind wander, you might think about like when a waiter rushes through a restaurant or a waitress, a server with like a glass on a tray or something, and you're rushing through the restaurant. What is the friction from the tray doing on the glass or whatever that's staying on the tray? Like, in other words, once both surfaces are moving, things get interesting. So we have to specify that friction from one surface onto another opposes the other relative to the one. Anyway, that's a detail, but that in cases like this, it's exactly what you would think. And in the lab, it's exactly what you would think. So what we do now is make the component free body diagram exactly as we did before. So I'm not going to run through that again. I'll say the component diagram is this. We have P sine up just like before. We have normal force. Sorry. We have normal force just like before. We have P cosine theta just like before. We have gravity pulling down just like before, but now we have friction going the other way, right? Opposing the motion of the block. So this is our free body diagram now, our component free body diagram now. Now this is starting to look it's starting to look like what you have in the lab. And it's starting to look maybe complicated, but but it's always the same procedure over and over again, of just going one axis at a time and leaving the axis you care about that you care about most for last. So I want to know the acceleration along the x-axis. So again, I'm going to go to the y-axis first. I'm doing F net equals ma along each axis, right? That's what I'm doing now. So I first do along the y-axis. What are the forces along the y-axis? Well, normal is pointing up. P sine theta is pointing up and mg is pointing down, just like before, right? So the normal is just like before. It's mg minus p sine theta. Okay, now now I just leave that. I go to the x-axis. The x-axis now has P cosine theta, and I'm just copying this straight from the picture, you see. P cosine theta is going to the right, but friction's going back the other way. Call that net, P cosine theta is going in the same direction as acceleration. So I'll call that positive. Friction's going, therefore, negatively. So we say P cosine theta minus friction equals MA in the x direction. Now, what is friction in magnitude? Always, I mean, this is a memorizer if you like. Friction is mu times the normal. That means it's roughness times how hard you squeeze the two surfaces together, if you like. Like that's what that means. So that equals ma in the x direction. I'm going to just go to the next. I'm just going to write. Okay, so I'm just writing the same thing again. P cosine theta minus mu times the normal equals MA in the X direction, right? Now, we're solving for AX. We're solving for AX, but it seems like we have another unknown, which is N. It would be an unknown if we hadn't had that other equation that we got from the y-axis, right? So secretly, what's really going on here a lot is two unknowns, two equations. And if we're not careful, it'll end up being like simultaneous equations, which is not always fun, right? I mean, okay, but if we go in the right order, we got the n information already from the other axis, so we can sub in. And this is what you're doing in the lab. It's just that everything's, I mean, this is almost a lab, just the lab is you're tilting, you're tilting your head. So we sub in n from the y-axis. So we say p cosine theta minus mu times mg minus p. Now, sorry, but right? I'm just substituting it from the other axis. All of that equals max. It's kind of like big old, well, so I don't want to confuse you. Like I took the information from the other axis and I'm plugging it in here, but I'm still talking about, uh, I'm talking about the x-axis here. And why? Like, why are they connected in this way? Like, why, and if they're supposed to be independent, why is the information from one applying to the other? Because that's the nature of friction. The whole idea of the formula, if you like, F equals mu times the normal, what that's really saying, what mu roughness is the extent to which this activity affects that activity. Now, I mean, sidebar, well, it's not a sidebar. Like this axis in space is totally independent from that axis in space. The laws of physics apply here at independently of the way the laws apply here. But the whole thing about materials occupying space, what it means to be rough, is that you're in effect linking the activity along this axis to that axis. That's what friction does. That's so the harder you squeeze things together, the harder they are to rub against each other. That's what's happening here. Now we can plug in numbers and hope sometimes hopefully that I gave numbers that actually are correct. I mean that actually work, and if not, I apologize, but here we go. So, so we're saying AX, which is what we're solving for, equals P cosine theta minus mu mg times P sine theta all over M, right? Because we're so 20 times cosine of 60 is 1/2 minus what I say. I think everything is a 2 in this problem for no good reason. Yeah, I just have 2 on the mind because I'm too far behind on your exams. Okay. Again, for anybody who joined late, I don't have your exams yet. I truly apologize. I'm not going to keep bringing it up, but you will get them. I've not forgotten. I'm just very behind. Okay. And the mass was 2. And G, oh, by the way, G is, you can call it 9.8 or you can round to 10, right? Not in labs. In labs, keep it, as accurate as you can. But you can round it to, but here's the key point though. Don't make it negative. G, once you're doing Newton's law problems, G is just, this is a pro tip also. G, but actually it's not even, it's like a rule. G is just a number. Lowercase g is just a number now that we're in Newton's laws. Whether it's called negative or positive will be taken care of. Like the force of mg might be negative, and we already said it was negative by making it negative in the original statement. Like you don't want to double negative it. I won't rabbit hole myself, but G is just a number. Don't make G negative 9.8. You're already taking into account positive and negative signs with your diagrams and the forces themselves. I don't know if you don't, if that throws you off, please text me or email me or whatever. But that's just a number, G. Okay. All right. Minus 20 times sine of 60, which is approximately 8.66, right? And this is all over 2. And the m's don't cancel out because there's no m in that first term, if you know what I'm saying. So it's 10 minus 0.2 times 20 minus Oh God, yeah, the numbers are going to be bad. Ugh, it's all right. I made the friction too big, but it's okay. You'll still see the point. Because this is sorry. One second. Oh, I had it right here. Sorry. Oh no, the numbers are not. No, the numbers are good. Yeah, right. So okay, so looking at the time, so we have 15 minutes. Okay, perfect. So the answer to the problem is like 2.32 meters per second squared. Notice that's totally reasonable. It's like smaller than 5. It's smaller than the other answer because now there's friction holding it back. All we did was the exact same procedure as the other problem, but we incorporated friction this time, right? Just as another horizontal force that went into F net equals ma along the x-axis. Only the catch is that is to realize that friction always, this is a memorizer, the force of friction always equals the coefficient times the normal force, which means the force of friction along one axis is always dependent on what's happening on the other axis. Hence, this procedure. Okay. Now, this is exactly, I mean, of course, you're solving for different things in the lab, and because there's a whole other big analysis. And I'll keep talking about the lab Wednesday, by the way, but I just want to help you set it up now, or so you understand. I mean, I know you're already into it, so you understand where all these diagrams and everything are coming from, and you don't just memorize them. This procedure is what we're using to analyze the situation in the lab. The catch is, just mention the lab and lose somebody already. Okay, what you have in the what you have, can you believe? Of course, I would have a whiteboard that's even jumpier and more spazzy than I am. All right, so is my dog. So the lab is a rough inclined plane, right? I mean, it's a slide on a tilt that has friction. So here's the lab. Now in the lab, first the thing is shoved up and then it comes down, right? Let's just for now, in case we run out of time, let's analyze the situation where the block is going up, like so it has an initial velocity, right? This is a situation. I'm going to skip this system schema for the moment in the interest of time and get straight to the you do a system schema, and then from that you do a pure free body diagram, right? And the pure free body diagram, if this is my picture, if in my case my tilt is like that, like your tilt might be the other way, but now this is my tilt. So my pure free body diagram is that gravity is pointing down, right? The normal force is on the tilt, right? The normal force means the push perpendicular, the push from one surface onto another perpendicular to the plane of contact between the surfaces. So right? So the track is hitting the block at this kind of angle, right? And if the block is moving up, in this case where the block is moving up, This is the up case. Then friction is opposing that motion, right? And pointing down along the plane, right? So this is my pure free body diagram. I'm just literally drawing an arrow for each force as it is acting. And by the way, notice this. We have 11 minutes left. Boy, people are dropping like flies. Um, Notice this is the pure free body diagram for the up motion. Notice there is nothing else in here because this is the diagram for any arbitrary motion, any arbitrary moment, instant during the blocks or the ball, whatever motion up the plane. This, in other words, that moment where you touch the block and you give it an initial velocity, that's a special moment. That's before the like the lab, the timing begins from the moment that ball is released from your hand. In other words, what your hand does your hand do anything in this lab? Yes, it provides the ball with an initial velocity, but it's not an ongoing force. It's a force at that one instant. That instant is before the lab begins. Honestly, the a force me I don't want to overdwell the point, but there's nothing that's pushing the block up the hill while it's going up the hill. It and in fact that's why it's slowing down, right? I mean, do you see my so there's no other force acting on the ball while it's going up. These are the forces. Now you can see that some of these forces are not perpendicular nor parallel to other ones. We need a component FBD, free body diagram, like we did in the exercises I started class with today, right? But now here's the thing, and I understand you know what I'm about to say, but well, anyway, we're gonna have to break up forces here. At least one force is gonna have to be broken up onto constituent axes. The question is, what force do we break up? Now, there's no rule about that. It's not like you always break up gravity or like in the last problem, we did not break up gravity, right? Um, but if there's a strategy, the strategy is always orient your coordinate system so that it aligns with the expected direction of acceleration, right? So we know we know that the ball is moving along a tilt, and specifically, it's going to accelerate along that tilt. Now, it's going to accelerate down. It's going to slow down while it's moving up. And while it's moving down, it's going to speed up, right? So the expected direction of acceleration is along the tilt. I'm going to make that my x-axis. And I specifically mean not only is my x-axis going to be along the tilt, but I'm going to make the positive direction down because I'm going to make positive down, whether this ball is moving up or moving down. I'm going to be consistent in both cases and make down positive because that's the direction acceleration is going to occur in. Now that's a strategy, but it'll definitely help you keep your minus signs straight and have a lot fewer of them. Anyway, so if that is the x-axis and then this becomes the y-axis, then it's gravity that is off kilter here, right? As many of you have already come to discover in the lab. In the last problem, gravity was fine. But now gravity is not fine relative to this coordinate axis. So I'm going to have to break up gravity and only gravity. Everything else, and that's the other reason, the other advantage is that then I will have to break up only one force instead of two. But so we break up, well, so we zoom in and break up gravity on this page, right? So with 7 minutes left. So if this is gravity, and I've got to break it up into an x component and a y component. right? That means I have to tilt my head. It means it means that this vertical line is now the hypotenuse of a big right triangle. That's what confuses a lot of people. And I'm telling you, I know we only have 7 minutes left, but this is the key. And this is like everything else in physics. You want to, if you've or don't tune out just because you've already memorized the answer and you think you're good with it, because because that won't help you for the future. I'm saying there's reason to be a little confused here at first. We're now, for the first time maybe in your life, you're going to treat a vertical line as a hypotenuse and make the legs diagonal lines. That's what confuses people. So don't skip it. Think about it for a second. I'm saying that when gravity pulls down, in this coordinate system, it's really doing two jobs. It's pulling somewhat along the plane and it's pulling into the plane, against the plane, right? Gravity is doing two jobs. It's sending the thing accelerating back down to the bottom and it's keeping it on the ramp. So one of these jobs is mg sine theta and one is mg cos theta. Oh, sorry. The hard question for everybody. So don't memorize. I mean, I'm not saying that the answer you got in lab is wrong, but what's confusing, well, anyway, I'm saying what's tricky is which to choose as sine and which to choose as cosine. And the answer is okay, and I think someone asked me this in this class. I can't remember if it was this class, but don't memorize with sine and cosine. In physics, don't memorize that sine always means y and cosine always means x. It's not actually true. That's not actually the case. What is true is that sine is always opposite and cosine is always adjacent. That's always true. So that means opposite or adjacent from the angle. Well, the tricky thing is, what do you mean by the angle? Well, definitely not the right angle, but which one of these is the angle? Well, in other words, the question is, here's the original plane. The original plane is inclined at a given angle from the horizontal. This is what we mean by theta. That's the knowledge we have with 4 minutes left. So the question is, in this diagram, which one of those angles, the top or the bottom one, which one is theta? The other one is the opposite of theta. Like one of them is theta, and the other one is the complement of theta. The question is which one, right? Well, there's many ways you can see this. And remind me, we'll sort of pick up on this. We'll start from here again on Wednesday and move forward. But it is like a really important skill to know in physics in general. And I can't emphasize it enough, but really what I'm really trying to say is I'm really talking any of you who are even confused, even for one slight moment in the lab, like, wait, where did mg sine theta and mg cosine theta come from? If assuming you've already seen that or the instructor already showed you or something. If you even had a moment where you were like, wait, what? Why is mg like mg sine theta and cosine theta? Then even if you got used to it, go back to that moment and acknowledge you're not crazy for being confused about that for a moment. What you would be crazy to pretend you were never confused. That would be crazy, and it wouldn't be a good idea. If you were confused for 1 minute, then remember that and bear with me now and try to like resolve it with me right now, and then you'll be good for the future. Okay? And I'm saying the reason we have an mg sine theta and a cosine theta is because we're tilting our coordinate system to line up with acceleration. That's why there's a sine and a cosine. Now, how do we know which one is which? Is it all depends on which one of these is actually the same angle as that one right there. And the answer is, I mean, there's many ways to see this, but the answer is since, sorry, since the plane is going like that, right? The plane is going like, in my case, it's going, and I know we have 2 minutes left, top right to bottom down. It can't be the top angle because this top line that's along the plane, positive x, right? That angle in there is measured from the vertical, but the angle that we were given in the problem was measured from the horizontal. So this top angle is the complement of that. That's 90 degrees minus theta. Therefore, this one is theta. There's other ways to see this, but in some ways, I think that's the simplest, right? Just think about that. That top angle is, I mean, in other words, the angle that you want. Well, I'll leave it at that. Therefore, the x-axis is opposite from the angle. So the x-axis takes the sine, and the y-axis therefore takes the cosine. So therefore, with 1 minute left, our component free body diagram becomes what you've seen in the lab. You have normal friction mg cosine, and in the case of when it's going up, mg sine. That's the up component FBD for that reason. And when we go down, I'm not going to do it right now. I know class is over. But when the ball is coming down, mg, all this logic is the same. The normal force, the logic is the same. The only thing that flips is that friction goes in the other direction when the ball is coming back down. Okay, so that hopefully that helps you somewhat. But if it, yeah, we'll keep talking about this on Wednesday. Okay, but thank you for your patience. You will get your exams back. You will. Not Wednesday, but you will. Okay, bye. Bye. Yes. Bye. Have a good day. Thank you. Yes, have a good day. Okay. I'm going to turn off the record.
Professor, I wanted to ask something.
Okay, wait. I'm here. Let me just turn off the record. Unless you want to be, no, you probably don't want to be.